Okay, thanks for the introduction. So what I am going to do is talk about bias and unwanted variability in high throughput technologies in some examples that I've worked on. And the hope is that you will see what has been done before, what problems have arisen before, because many of them probably will show up in some form or another in any kind of high throughput technology, including proteomics or whatever else you're looking at. So that's the hope. All right. So I want to motivate a little bit the talk to talk about the importance of what I call interactive data analysis, because today you have this tendency for people to want workflows that kind of are automatic, do the data analysis automatically, and you see a lot of the papers when the first published describe new technologies, new applications of technologies. They'll include some workflow, and they'll have little pictures like this. That basically, if you just want to summarize them all, they are basically saying just give us your raw data, we'll process analyze it, and at the end you'll get something that lets you publish some result. So that is, I think that the tendency to want to go straight into this mindset, into just being able to turn some crank and leave the data analysis to a predetermined analysis pipeline can be dangerous. There's a quote from Tukey about how important it is for thinking humans, to always be involved in the process, and that's what I want to show you examples of this, of cases where there was a pipeline, and by exploring the data carefully, we found some problems that made it clear that the regular pipelines didn't work. That then led to methodology that solved that specific problem. So I'll talk about both how the problems were found and the statistical solutions that were developed for those problems. So the other set of slides that I like to use to motivate this, especially for those of you who are doing the analysis side of this, is kind of give you an idea of how important I think what you're doing is. The analogy I try to make is to the discovery of microorganisms and many other things that were not visible to the naked eye. So this is what a lot of scientists at the time of when the microscope was new were seeing when they looked at, say, a drop from a puddle in some lake or whatever, some puddle or some river or lake, and there was this one person who improved the microscope. He didn't invent it. Van Leeuwenhoek didn't invent the microscope. He just had ways of making it better, and he was able to see what other people couldn't see. So he discovered microorganisms. He discovered a bunch of other things too. He was the first one who actually was able to see them under the microscope. So today, I think there's something similar going on with high throughput technology, where you have the raw data coming out of these things is basically most of the time out of focus, and just to start, it's just a bunch of text files. It's just a big bunch of sequences or a bunch of intensity numbers. So definitely you can't just look at it. You need somebody to turn them into something you can look at. So right there is one of the tasks of the analyst is to do that. But then there's also, you have to sift through a bunch of things. Like if you're doing a genomic analysis, you sift through the genome looking for something interesting. That is also part of the process of putting things into focus. You can't look at everything. You have to pick what you look at. And there we can use the ideas of statistical inference to decide, like, what is worth looking at? What could be due to just noise? What is more probably some interesting signal? So with that said, that's kind of the general idea of what I'm talking about, the general motivation for what I'm going to talk to you about. So I'm going to do it I'm not going to give you some big unifying theory of anything. Instead, I'm going to show you some examples. And they're they're from microarrays, from sequencing, from different things, different applications of each one. But the overarching message is that you should explore data, analyze data carefully, interactively, and not just accept whatever the latest pipeline is without being careful and exploring data, checking, doing diagnostics. All right. So feel free to interrupt me. We have an hour and a half, and I have enough for that, but I'm happy to stop because it's just a series of examples. We can stop early after the first example, after the second example. So just make sure that you ask questions if you don't understand something I'm showing you. All right, so here's the first example. This is a PCA plot, MDS plot, same thing. We're basically showing the first two principal components of a matrix that has the genes on the rows and samples on the columns. So each point here represents a different RNA. This is RNA measurements, transcription. So each point is a sample, and it's a summary. It's a two-dimensional summary of a 20,000 dimensional vector that represents the gene expression pattern. And each point is a sample, and this actually comes from a public repository where I picked 5 different tissues. The reason there's more than 5 points is because for each tissue there's several replicates. So imagine now that let's think back to the microscope analogy. This is the picture you're seeing, and you don't know at this point. This is back before we knew much about how tissues are different or whatever. We didn't know that gene expression was different from tissue to tissue. So if we were going to discover that using this data, you wouldn't really necessarily see it here. So if I show you this, and I ask you to point out where the 5 tissues are, it's not that simple. Right? You see some clusters, maybe 1, 2, 3, 4, 5, 6, 7, 8. There's more than 5 clusters. So what is that about? So now I'm going to fill in the tissues with color. So you can see now there's 5 tissues. And if you just base it on this, can everybody see the colors? I don't know if you want to turn off the lights or something. So the distance between 2 points in this plot, this is the first 2 principal components, which explain probably like 25 to 30% of the variability. So the distance between 2 points in this plot, right? So the distance between this point and that point is it's a crass approximation of the distance between the 2 gene expression profiles, because again, these are the first 2 principal components. So this sample and this one are pretty far apart, and these 2 are pretty close. So we're saying that these 2 colons are very far, but this colon is very close to this. I think that's endometrium, and that is not in accordance with what we know today about how gene expression differs from tissue to tissue. So there's probably a problem with this data. Now this was, we ran what at the time was the right pipeline. It was was recommended by the people who sold the arrays. We ran it through that, and then we get this plot. All right, so when I first started working with these data, this is a long time ago, 15 years ago, more than that, that's 18 years ago. We saw many, at the very beginning, we saw many similar problems where the plots that you made didn't quite make sense, didn't quite agree with what we knew about biology. So that's when we stop and say, well, let's look at some exploratory data analysis plots. Let's go back to something more closer to the raw data and start looking at what's going on. So this is a very global picture. It's just the first 2 PCs. There's only 2 dimensions for every sample. So let's get closer to the raw data, and let's take 2 points, and let's make a plot showing the gene expression estimates for every single gene. And so we do that. And now we see this plot. This is a very useful plot to know about. If you're working in genomics, you might have covered it already. It's called, in genomics, we call it an MA plot. Before that, it was called an Altman plot. And there's another name. That's like the Tukey difference average plot. But they're all, basically what it's doing is it's instead of plotting, we're looking at two things now. We're looking at just two samples. Because we want to be able to look at all the genes. It's going to be hard for more than two samples at a time. So the first thing that comes to mind is just make a scatter plot. But this is a more useful plot because what we're really interested in is the difference between the log ratio between every gene between the two samples. So that's in the x and the y axis. That's the log ratio, gene expression between sample 1 and sample 2. And on the x axis, we have the log average. So for those that know a little bit about linear algebra, this is the rotation of a scatter plot. You take a scatter plot and you rotate it on its side and you stretch the axes a little bit, but that's basically what it is. So it's the same information as a scatter plot, but it's very good at showing you what you most care about, which in this case is the differences between two things. So it's very common to use this plot instead of a scatter plot, because again, it shows you more than a scatter plot does. I'm gonna show you another example of how that is helpful later. Okay, but back to the question. So this is a plot of just two samples, and this one is it's actually not one of these. It's an experiment that was run just to check if the technology was working, where we put the same RNA sample. We basically took two random samples of the same RNA of the same sample. So you should have basically the same thing in both arrays. They're called technical replicates on two microarrays, and then we added for 16 genes. And experimentally, we added more transcripts to one of the samples compared to the other. So it's only for 16 genes. So what we should be seeing here, if we weren't told anything, and we're asked to find those 16 genes that were different, that were actually known to be different, we looked at the log ratio. We will look for those that are the biggest ones, the biggest ratios, the biggest differences should be those 16. Because everything else should be roughly the same. It's the same RNA sample. Those 16 are in orange here. And we see a bunch of other stuff that looks bigger. And that is a problem. Right? So if we were asked to find those 16 without knowing which ones they were, we wouldn't have guessed these 16. We probably would have started from up here or down here and start moving down. It would have taken us. We would have had like hundreds of false positives before we got to the first true positive. So that's the problem. So one of the things that we see is that when the expression is low down here, it seems to be this explosion of noise. Low expressed genes, that is a problem. So if this is your data, what you should see is these orange guys up here and all the black points near 0, and that's what you're getting, then there's a problem. All right, so when we first were seeing this, we started asking people that were running the experiments, why is this happening? We got different answers. One of the most common ones was that the company that was selling these microarrays was no good. They should just forget about it. And if you just base it on this plot, you're probably right. Another thing we heard is that that's how biology works. There's just noisy and all right, but we looked a little bit more into the problem and eventually found an explanation. And I remember it was like Appendix D of the manual from the company that explains the statistics involved in the whole process. So you had 500 pages of the biology, and then at the end a little appendix section on the analysis. And when you looked at that, you learn that before you even get to the measurements that are used here, there was another step that was done. There was even raw data that we didn't know about that was used before that was summarized in some way using some statistical ideas to get to that value that we were given from our collaborators. So here's what it was. Here's what was going on. And this actually, you can see, pictures like that where you have the bigger variance for the low, very common in genomics, and you're going to see why now in a second. It's actually a very simple explanation. But you'll see why it is. Okay, so what was happening was that when they were developing the technology, they realized that the units that were the measurement units that were used to measure gene expression would report an intensity. It would report a number when they knew nothing was there. So even when nothing was on the chip, even when they knew that gene was not expressed, didn't matter. They always got some number, and they were pretty high, up in the 30s, 60s. And they noticed that if you they had different ways of measuring the same gene. They have different what they call probes to measure the same gene. They would give out different levels of this background noise. So to solve that problem, so that this is the model, you can write it mathematically like this, where you want to estimate some number that's there, that's the gene expression amount. But when you observe the intensity from the technology, you actually see a background level that's added to the signal. So when you see Y, you don't know what part is beta and what part is alpha. You have no way of separating those two out. So what they did was that they added a second measurement that was supposed to only measure the background. And this is very common in experimental biology, where they know there's a background level, so they try to measure it with some other measurement unit. And so now you had, in theory, you had a measurement of the sum and then a measurement of just the background. So if you subtract them, then the problem should be solved. Now the problem is that when it's not quite that clean. So here's a plot. This is in the log scale, and we show everything in the log scale because, for better or for worse, people we were working with, and then the whole field was looking at ratios, log ratios. So when you're looking at ratios, you should use the log so that it's symmetric. So we show things in the log scale. We care about log scale measurements. There's other reasons to use the log, but that's just what we do. So here's a plot of the log intensities in an experiment that we constructed, where we asked our collaborators to make sure that there was no beta for anything. Basically, make an experiment where no gene expression should be measured. So it's a completely negative control experiment. So in that case, there's no beta, so you should have these two measurements show the same thing. They should both be alpha, and this is the plot of that. So you can see that the technology is doing something right, because this is pretty highly correlated. But it's not perfectly correlated. The correlation is about 0.7. So that means that these two numbers aren't exactly the same, they're correlated. The background levels. They're highly correlated, but they're not the same. And now once you see this, it's actually obvious what's going on. Not completely obvious, but if you know a little bit of math, it is. If you have a model like this, then it's pretty. This is just a very crass approximation. Not that crass. It's not that bad. It's an approximation of what the variance of that corrected signal that they use is going to be, and it's going to be inversely proportional. If you want that, you can use Taylor's theorem to get that. It's going to be proportional to the signal, to the actual expression level squared, 1 over that, proportional to the reciprocal. Okay, so this is all math. There's no biology here. This is just a fact. If you have this, the variance of that is proportional to the reciprocal of the signal, which is exactly what we were seeing. Right, you had this curve. I can go back and show it. This is an estimate of beta. If you draw 1 over beta squared, it's going to look like this. you can see that the mathematics is actually predicting the variance. So that means it's not biology and it's not the technology. It's the fact that they do that. That's easy to change. That you can change in the code. It's free. It's almost free, except for the time it takes me to do it. So our group, other groups, similar, they had similar solutions where they said, don't do that. Do something else. So you can get a little bit more sophisticated with statistics or not. You can do ad hoc things, but you can develop a correction where you're guaranteed not to have the variance go up like that. So that's the RMA method that Olga was mentioning. Is a solution to that problem where you correct the signal, but in a way, in a statistical way, that guarantees that the variance doesn't blow up. And now this picture, this is the same without changing the experiment, without doing anything, and just changing the statistics, the code that turns the raw data into the final measurements, turns the data into this. So now, if I ask you to find the 16 orange points, and I just gave you these values, you would go 1, 2, well, that would be 3, 1 mistake, 4, 5. So you would get like out of the first 10, you would get 9 right, as opposed to 0 in the original, with the original data. Okay, so now back to this. So this is just an experiment. When you could say, well, that's artificial analysis. Okay, so now let's go back to the original experiment from real experimental data with tissues. This plot was made with the original algorithm. Once you run it with a new one, it turns into this. And now you discovered, we already knew it, but we would have discovered that tissues have similar gene expression profiles, and it's perfect. If you do a k-means clustering or whatever, I think you probably get it perfect, almost perfect. Now you might get these two separated, but much better than this. Okay, so that's the first example of how digging down into the data, finding a problem, making it better, actually had an improvement. Now that this algorithm became the default. Even the company itself changed their options so that you can run it if you wanted this instead of that. And now it's part of if there is a pipeline, now this is part of the pipeline. Okay, now another thing that we were doing that I didn't explain and has to do with normalization, which is currently I think one of the toughest things in genomics is doing normalization right. I'm sure it's the case in proteomics. So what is normalization about? So this is a different data set. Here we have a box plot of the intensities, log intensities of 5 technical replicas. So the same RNA, you take RNA, you split it randomly into 5, and you run, in this case, a microarray each one, and you get whatever you get, right? You get the measurements you get. So these are box plots, and you can see that they're not the same. They should be the same. So before I was showing you gene by gene, now I'm comparing the distributions across samples. So this is a box plot, a very, very useful plot. And here's another very useful plot, similar to the box plot, except I'm showing you the densities of those same 5. And you can see that the distributions are changing. So you start out with this statistically the same material, but then you look at the distributions, and they're different. Not only are they shifting, like you see how the green shifts over to the right by about 50 to 100% bigger. So it goes from here to here. That's a change of almost 1 log 2 scale. But there's another little difference. It's not as simple as just a shift. You see this green thing has like a second mode that you don't really see in these orange and green ones. You can kind of see it in these. So it's not just that it's shifting, it's a little bit more complicated than that. So if it were just a shift and we know that they should be the same. That's easy to fix. You just make them all have the same median, and then you're done. But it's not that simple. And to see the consequences of this, here are the two. Yeah, now I'm going to show you just two samples. You can see that the green and the orange samples, and now here's the MA plot of those two. Notice what happens. It's when I look at the MA plot, one obvious thing that we do see is that the whole, the second one, I guess this is the green one, this is orange minus green, and you can see that it shifts down. Yeah, we know that because orange shifts down to green. So there's this global shift going down. That's this to this. But there's another thing that happens. It's that the shift is not as big for the low expressed genes. So if I were to do the naive thing of just making the medians the same, then this would be what I would end up with. Right? So now, okay, I fixed that. They're now aligned roughly, but you can see that they're now roughly aligned, but there's still that weird curve. So if I were to rank these genes in order of which one's more different in the orange versus the green, I would get this bias where all these guys, the low expressed genes, appear to be bigger in the green, and then over here, on this side, we have all the genes that appear to be bigger in the orange, and that can't be right. So the message I'm giving you here in this picture is that simple methods aren't always enough. So let me just show you one solution that exists for microarrays that is also being used in other fields called quantile normalization that works pretty well in many situations to solving this problem. So the idea of quantile normalization is quite simple. Here we made the medians the same. How do you make the medians the same? You subtract the medians from both, and then you can add back something to make them be in the original scale. Right, that's simple. So now they have the same medians. Very easy. So what quantile normalization does is it actually makes all the quantiles the same. So if you have a matrix with a bunch of samples, you order them, you order each one, and then you take the average of each row and substitute in that average into each row, and you end up with a matrix that has the same distribution. Then you order it back to the originals so that the ordering within array are the same, or within sample are the same. Basically what you're doing is assuring that every single sample has the same distribution. I'm not saying that should always be done. Definitely not. Sometimes you know that the distribution should be different. So if you make them be the same, you're washing away important information. But let's see what happens here where we know it should be the same. So here's roughly the same. Here's an example where I have, again, genes that were added in. Now I have more. So all these green ones were added in to be different. They're supposed to be bigger in the orange against the green. So in the previous example. So these should be different, and the black ones should not. So in a perfect world, the black points would be at 0, and the green points would be bigger than that. So now what I'm going to do is I'm going to, whoops, what happened? Oh, I missed that. So I'm missing a slide. So if you normalize these guys, I owe you that slide. This does get flattened out, and then the green ones stay different, which is the key, the main point of this plot, that when you quantile normalize, you still preserve some differences. It doesn't make everything the same. It makes the distributions the same. So I owe you that slide. I have it somewhere here, but I can show it to you later. Okay, so that's one type of normalization, quantile normalization. It's being used in many fields, but it's not always appropriate because if the biology tells you that things should be different, the distribution should be different, and force them to be the same, you are washing away an important characteristic of your data. Okay, so that was a brief discussion about normalization. There's much more. There's now, especially with the sequencing data, there's a lot more challenges related to normalization. It's current research. Okay. So the next topic relates to something that we'll call the batch effects. And again, I'm going to use an example, a real example. This is actually a paper that was published in Nature Genetics. And here's one quote from the abstract. So what they did is they took blood samples from around 200 and I think it was 209 individuals from different ethnic groups, and they ran the data through the standard pipeline. And now we're going further than pre-processing. Now we're actually going to the next step of analysis where they're doing inference on each gene. And then they do multiple testing correction. I think you're going to hear more details about the different ways of doing that. In this case, they use Bonferroni correction to end up with a list of genes that are differentially expressed between two ethnic groups. And they come up with a pretty surprising result. That the quantitative phenotype differs significantly between European-derived and Asian-derived populations for about 1/4 of the genes. That's very surprising to have that happen. You have blood. You would think that blood across humans is it's not the same because different people have different blood types and whatever, but you would not expect it to be that different when you compare two populations, which themselves are variable within each group. All right, so let's look at the data. So this data set is available. It's publicly available. You can get it. Here we downloaded that data set, and we made a PCA plot. So here are the 209 points, and they're colored by the ethnic group, and the PCA plot seems to confirm what they were saying. There's clearly a difference. In fact, it's the first principal component. If you look at the first principal component, here are one ethnic group, second, and then a third. In fact, you can run the analysis on this data. You can run a t-test, apply Bonferroni, and you can confirm the results. If you use something, for those that know about Q values or false discovery rates, if you use something like false discovery rate or Q values, and you set a cutoff of 0.05, you get like 80% of the genes are differentially expressed, which is in agreement with this picture. I mean, if the first principal component is basically the ethnic group, it's got to be a big number of genes that are different. Okay, now this one's a little bit harder to explore. It's a very surprising result. That gives us reason to check carefully if there maybe was something off in the analysis. You read the analysis, you can repeat everything, everything's fine. The pipeline is the standard pipeline, everything's fine. Now, when we look at this picture, now here's where Tukey's quote comes back of seeing things that surprise you in figures. There is something strange about it. So if you have two ethnic groups, and you say that there's all these genes that are differently expressed, you wouldn't expect there to be so much more variability in one group compared to the other, especially given where these populations are from. So there's another thing that catches your eye if you look closely enough, and once you become trained in looking at genomics data, you start seeing these things. You can kind of see that there's subgroups. There's a little subgroup here. There seems to be another one here, then this one, and this one. You can almost see like 4 or 5 subgroups, right? 1, 2, 3, 4, maybe 5. And that is not explained by this. So what is that? So this is there was a group of statisticians that were looking into this, and they first of all they took advantage of the fact that in the raw data files which are made available, you can actually get a stamp from the header that tells you the date in which the file was generated, which is probably around the time that the experiment was done. So when you do that, when you look at that information, so now what I'm going to do is I'm going to change the color to represent the year in which the sample was run. You see something that is worrisome. So now we see that this was run in 2002. These were run in 2003. These were run in 2004, 2005, 2006. So that's an alternative explanation for why these genes are different. So when they compared this group to this group, they weren't only comparing ethnic group 1 versus ethnic group 2, they were comparing 2003, 2002 to 2005. Nice. Yeah, go ahead.
I don't know if this was microarray or...
This is microarrays.
Did they run the same microarray file?
Yeah, same platform.
Same platform?
Oh, what happened? The same platform, but clearly that there's some within the platform. There's still probably something changed. The reagent, who knows? Okay, so this is in experimental design or in epidemiology. When something like this happens, we say that there's a confounding factor here. Year is confounded with ethnic group, and it's almost perfectly confounded. With the exception, I think, of 3 samples, it's like one group was done in 2 or 3 years, and the others were done in other years. So when it's perfectly confounded, it's hard to tease apart: is it the ethnic group or is it the year? But here, exploratory data analysis gives us further insight because there's nothing special about years. It's not like this relates to the question you were asking. It's not like the company comes out with a new product every year. But in labs, those that work in labs, you know that every once in a while you change this or that. You run out of this and buy a new one, etc. Technicians are fired or they have to go somewhere else. You get a new one. So if we make it a little bit more, the resolution a little higher, and we look at months, we might be able to see something. So what I'm going to show you next is a plot of the first principal component stratified by month. Yeah. I have that plot somewhere, but it's probably easier for me to describe it than to go find the picture. The p-value distribution looks like everything's over here on the small ones. I can draw it, I guess. Can you see how I draw it here? It looks like this. It's kind of what you expect. It looks like that. So, well, no, yeah. So you're saying that from the p-value distribution you can somehow see batch effects? I mean, this is one way you see them is when you have an extreme case like that. But yeah, you can't from the from the histogram of the p-values. What you would conclude is that I would conclude that much more than half of the genes are differentially expressed when you see something like that. Okay, so this is the plot of the PC1 versus month, and now if you just stick to the orange, that's the same ethnic group. There's a big jump in this month. It jumped down, and then there's another jump around this day, and then it kind of stabilizes. Right, so if you look at this period of time, two ethnic groups aren't that different. Oh, and by the way, there's one of the few cases that's not completely confounded. See that orange? Is it? There's another one somewhere. No, I mean, that might be it. And with just 1 point, you can't do much. Because if they weren't confounded, you can try to estimate the different things, but not with just 1 point. All right, so when I see this, now I'm convinced it's probably the date, not biology. But that paper is still published. There was a back and forth, but it's still published. It's like a disagreement between a group of statisticians. Is what the conclusion was from the journal. Huh? I don't know. Probably not. I think most people just say it's not going to show anything. It's not worth them.
It's not worth the money.
Yeah, and I mean you could. Yeah, that's what I think. Yeah. It's not worth the effort. Most people see things see a plot like that and they become convinced it is the date. Okay, but it is, this is probably something that, now that you say that, there are probably other studies that didn't actually write about the ethnic groups, but they are there. So if you have like a gene expression experiment that was done on like the HapMap data sets or whatever, you could actually try to do this.
That's what I was thinking. Out there where you could at least.
Okay, so let's talk a little bit about the stats behind all this, and I'm going to also present some solutions that have been proposed for this, for dealing with these problems. All right, so here's a model. When you do a t-test, which is what was done there, and it's done in many circumstances, also with some of the more modern approaches for RNA-seq, where they do other more complicated models that, say, use negative binomial. They do tests that aren't t-tests, but they're in the same vein, right? They're estimating a parameter that measures the difference. They estimate its standard error, and they look at the estimate divided by the standard error. So in the case of t-test, what you're modeling, what you're doing is, in your head, you're saying there's two groups. There's some baseline level for like the first group, the reference group, the control group. And then in my second group, there might be a difference. You do this gene by gene or weight by weight or methylation site by methylation site, whatever you're doing one by one, you're doing this. So then there's measurement error. So what you're asking is this number, is this parameter different than 0? That's what you do when you're doing a t-test. You test for that. So you want to know when is this not 0. When it's not 0, that means there's a difference, and that's the ones you report. So what we do when we do statistics is that we say we take the average of the data from group 1 and the average from group 2, and that difference should be about beta, because these guys cancel out. They're measurement errors, so they cancel out the 0. The alphas cancel out, and you're left with beta. So by comparing the two averages, you get close to what you want to find out if it's 0 or not. Now, statisticians do even more for you. They tell you about how much can this vary by chance, and then they say it's about this much. This is the variance of the population of this guy, and then it's divided by the square root of n. Mathematics tells you that. So now you can see if this is 0 now. So if you know what beta, you have your estimate, and you know how much it would vary by chance. So now you get an idea of how likely is it to see the number you saw under the null, and et cetera, et cetera. That's what you learn when you learn basic stats. Okay, now the problem is that when we have what we're now seeing, these batch effects, that model is no longer useful. So these batch effects are all over in genomics data. It's very rare to find a case where you don't have some kind of groupings that aren't due to what you care about. The case we just studied is an extreme where you had this is what I'm going to be calling the batch effect. You had an effect that was completely confounded with the group. So here we had for group 1, ethnic group 1, you had this is an alpha, sorry. Alpha. had alpha plus W1, that's the year effect. This is a 2002, 2003 effect. And then for the second group, you had the 2004 effect. So the problem is that now you can't distinguish when you look at a difference, like we did before. This isn't true anymore. It's not true because you have the W's. This is what you have. This difference is the actual biological difference, if it's there, plus the difference in the batch effects, in this case, the years. How do you parse those two out? You can't, in that case, in that particular case. So now because of this guy, you can't use their standard inference. So there's another way to think about this that is actually quite commonly used these days. It's instead of thinking of W as a fixed term for the statisticians in the room, you think of them as random effects. And if you're thinking of them as random effects, it's not a bias anymore. It's just that the variance of W is you're not including it when you estimate the usual t-test variance. So then that's another way to think about it, is that you're underestimating the variance. So this is the deterministic way. You have a bias. The second way is you are underestimating variance. Those two are equivalent in some ways. It's just different ways of thinking about it. Okay, so let me show you some. So these batch effects are not unique to high throughput data and genomics data at all. They're all over the place. You see it. Some people claim that Tom Brady's footballs, that was a batch effect because they measured it. They measured the balls with two different techniques, and they were a batch effect, so that's why they seem to be deflated. That's a very New England example. Then there's another more complicated batch effect, I think, is the way that some of the posters missed what was going to happen in the elections, because there was a batch effect, which was the Rust Belt. So a lot of these predictors of who was going to win the election, they assumed that every state voted separately, independently. So when they said it was a 95% chance or whatever it was, that was under the assumption that every state was a random process that didn't depend on each other. But then what happened was, when you have groups of states voting together, that makes this go up. Well, here's an example from physics from a long time ago. So these are the published measurements of the astronomical unit, published with confidence intervals. So there's the estimate, and there's the confidence interval. There's a paper from 1972 that talks about this. They have a little table which I turned into this plot. So they basically have a table showing you the estimates and confidence intervals for a series of papers about this measurement. So this is estimate in 1899 or 1990 or something, and then here comes the second measurement that now has this confidence interval, and there's something weird going on, because either the speed of light changed or something's off in these things. And it could, clearly these two can't be right, but you could say they were right if their intervals were bigger. This is the current estimate, is this dotted line. So then you see as other measurements come in, you can see that, look at these two. Again, the speed of light changed from here to here. So what is going on here? So there's a batch effect. Each lab has its own, you can think of it as bias. These confidence intervals come with internal measurements. The same lab is measuring it over and over again. I don't know how they do this. They wait for the sun to come out and then hit their stopwatches. They do it. They must have been doing it more than once. They get a confidence interval, and that's what it is. So whatever batch effect, whatever bias that lab has, they have it every time. So it doesn't make their variance grow. that would be the W in the previous example. Each lab has their own W, but it's in every single one of their measurements. So they don't see that, they don't ever see the W. You only see the W when you look across experiments. So in genomics, we get to see that. We have like all this data that we get, oh, look at that. But with low throughput technologies, you'd only see it, 60 years later, after 60 labs have published that there is a lab effect, right? This is the variance of W explains this variability. The variance of epsilon, the measurement error, is only that big. That's why all these confidence intervals are so small. So, yeah, question?
Is there an association between, like, the longitude or latitude of the labs?
Oh, good question. I don't know. You could look at that, although most of these are probably in Europe. But you can, it's in the paper. In the original paper, they tell you the actual lab. Yeah, but this is the same lab. Yeah. And then there's another case. These are the same. And another thing, something to notice about this is that those are pretty damn close to the actual current estimate. I mean, that's amazing. The fact that they got that close, I mean, look at the scale. It's not, this is 1900s. You can't even do it now. They were doing it in 1900s. The point is that their measurement, their variance estimates were wrong. That's all it is. Because once you can see that they're getting very, very close. Okay, so all right. So now how do we deal with this fact that we have these groupings? In the case of in this experiment, it's something having to do with the lab. And the original one we saw, it also has something to do with something having to do with year. This is a correlation matrix for those 200 and some samples I just showed you from the different ethnic groups. So what I'm doing here, in this plot, I have 200 samples. I compute the correlation between each one. Now I'm assuming there's no such thing as ethnic group effects. I'm just computing correlations between each group, between each sample. So there's 200 squared little pixels here. Each little pixel is a correlation between two people. And then I'm ordering them that way. So it's the same order. So you see that red line in the middle, that's the correlation of someone with themselves. So that's going to be 1. I'm ordering it by time. So can you see the years in that picture? There's 5 different years. It's not that obvious that there's 5 years in that picture, right? You can see there's definitely this is probably something that the technology did change here. This is Affymetrics. They probably did something in around 2003 that really changed things. Because you have this group and then you have this group. And then some of these in the middle are probably arrays that were bought earlier or later, but they were run at other times. But then once you get past that big change, now you look inside and there's other ones. Look at this square. That's another batch. And then there's this one, and then this one, and now inside here there's this one and that one. It's very complicated. It's not just year, it's not just month, it's some really complicated structure that induces correlation. And pretty much every genomic experiment that is big, that takes a long time to generate the data, is going to have something like this. And it might not be year, it might be some other thing. It might be the temperature in the lab, or who knows what. We don't know all the details. But the point is that when you have this, for the t-test to work, this can't happen. The t-test assumes independence. Parametric tests that do, if you say, I'll just do the non-parametric test, they also assume independence. So do permutation tests. All these things assume independence. So you have to deal with this somehow. All right, so let's look at this, and let's look at some of the solutions that have been proposed. These are the papers. It's 4 of them. Now there's more papers. This is like something that a lot of people have gotten into because it's a hard challenge to deal with. I'm going to show you some of the techniques that exist for this. All right. So to demonstrate the techniques that are available, the ideas that are available, I took a subset of that bigger data set to illustrate. And the reason I don't use the original data set is because when you confound your main batch effect and your main outcome of interest, there's currently nothing that statistics can do for you. Maybe that'll change, but right now, there's no solution. When that level of confounding is present, there's just no way of parsing out things. However, when it's not completely confounded, then there's hope. So I made an example that's not completely confounded from that data set. Instead of ethnic groups, I'm comparing sex, female, male. But I did confound it on purpose. I had the males get confounded with June. There's 9 in June, 3 in October, and the females were 9 in October and 3 in June. So it's not perfect confounding. There's some confounding. See, so now we have a chance. Now we can try to estimate the month and separate it out from the sex effect. All right, so there's some data. This is not a cartoon. This is actual data from those experiments. It's a subset of the genes because there's 8,192 genes. But here I'm only showing you maybe 50 or so. Just picked a few genes just to show you an example of what it looks like. But in that picture, the genes are on the rows, and the columns are the samples. Can you tell where are the males and the females, and what chromosome is where? Can you see something, or maybe I'll give you some hints. So here are the males, or maybe So here are the females, and here are the males. What chromosome is that?
Probably
Y, right? The Y chromosome, males have some expression and females they don't have it. So that's the Y chromosome. So it's work. These arrays work. They do work. They can see things that are there. All right. So there's males, females, 12 and 12. That's making sense. Now, can we see June? October. June is red here. These genes go up in June. 9 and 3. And where's October? Here's October. And in these genes, it flips. These genes don't like June. They're off in June. They're off in June and on in October.
Is melanin production in there?
Yeah. Well, but no, because then you have within... Oh, melanin production, I see. Okay, so there's your confounding, okay? So, what do? How can we solve this problem? So here's the first thing to notice. This is the t-test. If you like linear algebra, you can write it like this. You can write the model for the t-test like this. It's just the linear algebra way of writing. The expression for a gene is the baseline. Let's say females are the baseline plus a beta if you're a male. So that will be. It'll be some number if there's a difference in that gene between males and females. So for the Y chromosome, that would be different. We might see some differences in the X chromosome too, because females have 2 and males have 1, although most of the time the females have one of them shut down, but not always. So you will see some differences in the X chromosome. So we should see beta be not 0 for X and Y chromosome, and it's probably for most other genes, they should all just be the same, because blood between females and males is really not that different. So this is the t-test model. It basically, the betas that are being estimated here are the reference gene expression level, which we don't care about, and then the difference for each gene gets a beta, the difference between males and females, and then there's measurement error, which is here. Okay, so this structure makes this happen. That explains that. And this guy is supposed to explain the rest of the noise. All right, so you have, for most genes, there's no sex beta, so it's just 0 plus noise, so it's just like this. And then for some genes there is a difference. The beta is not 0, so you have red and blue. The problem with that model is that these guys, if you compare this to this, it's going to say, yeah, those genes are higher in males. There's more red here than here. But that's not because of the maleness, that's because of the Juneness. Right? That's a problem. That's not explained by that epsilon. This epsilon says this is supposed to be independent noise. But that's not independent. There's correlation. So if you do a t-test, you get, I was asking about the histogram for the p-values. This is the p-value comparing males and females. These are the p-values, the histogram of the p-values, and you have thousands. Is it 1,000? Yeah, it's thousands. Right, so all these are significant, and that's and these are not chromosome X and Y. These are all the other ones. So that probably has to do with the comparison of June, the fact that you have more males in June. These are the chromosome Y genes, and you can see that out of the 9 plus 4, out of the 13 genes that are in chromosome Y, most of them have very small p-values. That's good. That's what should happen. These guys don't. That's probably because those aren't expressed. Not all chromosomes are. Not all genes are expressed, so they're not different. They're often both males and females. But this means we're doing something right. This means the batch effect is getting us. It's resulting in all these false positives because, again, we're making all these things. They're higher here than here, so it comes out significant. All right, so there's the. Oh, I missed one. Okay, I'll show you. I'll tell you about it, even though I didn't include it. Okay, so there's another solution. Some of you might have already thought about it. Is you can add another column here that says month. So you say the gene expression is the sex effect, the baseline, the sex effect plus the month effect, and we estimate both of them. When you use that, it gets a little better, but it doesn't completely get rid of the problem. And the reason is, okay, so you get what I'm saying? Like you just have a parameter that says June versus October, and that gets rid of that should get rid of it. But the problem is, the reason it doesn't work perfectly is because it's not month. Month isn't what's driving this. Month is a what we call a surrogate for whatever it is that's driving it. So here's again those correlation plots. This is ordered by females and males. This one's ordered by date. You see the 6, that's June, and then it flips to 10, that's October. They're ordered by date. If the batch effect was just the month, that correlation plot would just have 2 squares, here and here. If that model was right, if the model that says the differences that are not explained by random error, it's just explained by the month, then you would have, again, just 2 sort of squares, like fuzzy squares, but you don't see that. You see sub-squares. Here's This one seems to be 20 on the 23rd. This is the 27th, so that could be something that happened at some date. And then in here, I don't know, maybe you have like a special case here. The point is that there's these sub structures that aren't as simple as just one. So that's the challenge, is that in general, we actually can't pinpoint a variable that tells us what's causing these differences. So when you like that, when you have this issue, you can't write it. You can't put it into the model. There's nothing to put there. You don't know what it is. You thought it was month, but it turns out it's a little bit more complicated than that. So the solution that is currently a lot of people are trying to make work. It doesn't always work that well, but it's a first try. It's to use what in statistics is called factor analysis. This is not new. It's like 100 and some years old, although the way it's used is new. In factor analysis deals exactly with this problem. Factor analysis says, tell me the structure I need for a linear model, like a regression model. Find me the structure that explains this correlation. So factor analysis is kind of made for this. The problem is that in factor analysis, there is no real difference that we care about. This factor analysis doesn't include this part. It just includes this part. What is this part? This part is saying, find me, for statisticians in the room, find me a linear structure that explains this variability, explains the correlation. For the biologist, it's basically finding a relatively simple model that's manageable that explains the correlations that we see. It's how you get it. It's a little bit hard to explain, but there's theory that tells you how to do that. So the reason it's not just factor analysis is because we actually have two things. We have the signal that we care about, and we have the correlation structure that we don't care about, and we want to adjust for it. So the idea from Lincoln's story is to combine those two ideas into one, and then fitting this model, which is not easy, and then now that's a subject of current research, how to do that, how to best estimate that. I won't get into the details of why it's hard, but it is hard. But if you apply this idea, you actually get a pretty flat p-value distribution, which is what we thought would happen, without getting rid of, well, you only get rid of one. We only get rid of one of the y-axis. So it's a big gain in specificity with a very tiny loss of sensitivity. So what these factor analysis methods do is they break up the data into, so here's the original data. It says here is this is the variability explained by the sex variable. So you get all the Y chromosomes, you get a couple of false positives, or maybe not, maybe those are genes that are different. And then you get the factor analysis part that explains the correlation. You see that it's not exactly months. It's like, for example, this sample here doesn't get included with the rest. You know, so it's a little bit more complex than just month. And then you have the random part, which now looks pretty random. There still seems to be some leftover stuff here, but it's much better than what we started. So once you break it up like that, this instead of these differences falling into here, they get extracted out, and now we don't report them as differentially expressed.
So where does this break down?
Oh, well, that's a great question. So where does it break down? So there's several ways it breaks down. One is that many times the signal is almost, it's too close to being confounded with the batches, and then it just can't distinguish the two. The other way it breaks down is that when you do this, you have to estimate. Now we're getting into the details of factor analysis. The way factor analysis works is it starts adding basically principal components until you explain enough of the variance. But how many you add is not obvious how you choose. If you add like 100 PCs, you explain all the variability, but you probably overdid it. So choosing that, it's called K here. Choosing K is hard. So if you put too few Ks, it goes into the thing, and if you choose too few, it goes. If you pick too few, you get too many false positives. If you put too many, you get too many false negatives. So then another way that breaks down, in my opinion, and is that this doesn't quite work. It's not really linear. There's no linear structure that explains what's going on. So that is still a simplified model. You still need linearity. And if it's not linear, if it can't be explained with a linear model, and you force this to fit, it will get some fit, but it won't be what you want. So now another how do we know that when it worked and when it didn't? That requires a lot of experience, like knowing what plots to look at the end. But one of the things that we always do is if we're reporting genes that are differentially expressed, or we're reporting regions in like differential methylation analysis or ChIP-seq, regions that are differential, at the end we always make a plot of just that one region. And sometimes if we're reporting 100 regions, we have 100 plots that we have to look through. But it's definitely something we need to do, because sometimes when you look at the plots, you can still see batchiness. What do I mean by batchiness? That you have in the plot you see subgroups within the groups. So you'll see like you're reporting, say in this case males and females, and I show you the plot, and you see that instead of seeing males and females like that, you have these subgroups of males and subgroups of females. Like I'm going to go way back and show you an example of what I mean by that. This is an example. There's something there that's weird. And sometimes even after doing all the batch correction, you still see things like that, and you wonder what that's about.
If that's brain, aren't there a lot of documented differences between male and female?
Well, yeah, no, this could be real. This could be some other thing, but I don't know what sex those things. I don't know what they are. Yeah, I'm just giving an example of what the visuals look like that makes us suspicious. Okay. All right, well, I'm going to stop there because it's almost 11:30, and I guess you might have questions. So I'll stop there. Yeah, so there's an SVA package that does it. There's RUB is another one. Does it? RUB stands for removing unwanted variability. So the SVA package, I think, also has. So the method that where you model the batch with a specific design. The most popular model is called Combat, and that I think is included in the SVA package. Yes, but RUB is currently the one that's most being developed right now. The SVA isn't really being kept up. It does what the papers say, but it hasn't evolved much.
Yep. I also believe lemma. In lemma, you can remove batch effects, and if you play with it, you can get it to visualize your batch effects.
But isn't it using like the combat approach?
Yeah, it uses combat.
Yeah, for sure. In Lima, you can just model it. Sure.
So I missed part of it, but maybe you said it already. So, in light of all of that, what would be your advice of the best practice in terms of designing experiments and also to do things which are probably manageable
Yeah. So with design, the first rule is obviously don't confound completely. That's that, it feels like you shouldn't need to say it, but you do. You should never have run your controls now and your cases later. That's rule number one. Then how do you avoid? Now the other rule that's a little bit more subtle is: do you try to block? If you know what the batch effect is going to be, you try to block something fancy. My recommendation is don't bother just randomize, because the problem with blocking is theoretically the most efficient design, but you don't know from the beginning what you're blocking. Like if you know for sure it's state, then yeah, you can make it. You can design the perfect experiment. But you don't. But what if it's something else that you didn't count on? So by randomizing, you are. It's kind of your best hope for catching anything. So yeah, so randomization. When you have an experiment, you want to know in what order to run things. You just randomly do it. So now that is sometimes impossible to do because you have to have some kind of grouping. But again, it's like as much as you can, just randomize what gets done. And what was the other question? Oh yeah, so what to use? So my own approach is not to use anything of this. I use none of these more fancy things. I try to stratify and then do the simple things, or do the simple things and then visualize the results.
Because the risk of overfitting is
Yeah. But I have used SBA and REB a couple of times where it really seemed like it was working. But I don't trust it I don't just run it and trust it. No. Yeah.
So for longitudinal studies, how do you feel about running a reference sample of sorts
That's
with
great.
every experiment?
That's another. I forgot to mention that. Thanks for bringing it up. That's another thing we recommend is to have like a reference that you run with every batch. And if you can do two that are different, that's even better. So if you have like, let's say, last time we did this with the lab, we said run liver and spleen every time. The same liver and spleen every time. That's a really powerful idea. It can, yeah. So some of the RUV methodologies are now designed to take advantage of such things. And with things like that, you can even try to fix the things for clustering for unsupervised learning. Yeah.
So there are times when you take the whole gene expression for all, the entire genes into the PC, you don't see a very good clustering. But you take a few, you don't see very good
Yeah.
clustering. But then you shortlist like a few significant genes, and then you do see some.
Sure.
So is that, if we see something like that, is that good? Or do we always expect to see differences between the whole?
It's going to be, nothing is expected. I mean, the possibilities of experiments and the possibility of biological realities of your data are endless. So I can't say what to expect and what not to expect. But what you're saying about so it's always going to be in context. When I do blood, when I look at blood, I just have this bias that humans' bloods aren't that different. So that was the bias. When you see those plots and you start seeing clusters, you start getting suspicious. And it turns out that we were right, that it was some other thing. Now, what you were saying earlier about the different subset of genes, that's definitely something that we do. We sometimes take the subset of genes that are the most variable, just kind of amplify whatever signal's there, as opposed to just having the whole matrix. But if you filter your genes using the data and then make a PCA plot, now you're into some circular stuff, right? If you filter your genes to be differential between two groups and then you do a PCA, guess what? That's going to be the main filtering, so that's not a useful exercise. If you filter your genes based on finding groups and then do a PCA, you're going to just find the groups. And that's no need to do it because you know what's going to come out. But subsetting genes to say, take out genes that have mostly zeros in some of these new RNA experiments where you have that, or taking the ones that vary the most, that's definitely powerful.
Okay, then my second question. So you showed an example of the ethnic groups. So the orange, green, and the blue plots. So unless I know that all the these orange group belongs to one particular ethnic group, when I see the PCA plot, how do I actually define that this is a group? Like how?
Well, if you don't have any notation that tells you what's what.
But like a PCA plot should actually give you some groups.
Yeah.
But when I see that, it's just too.
So that's So many times when I start analyzing data for new project, many times the first thing I do is look at the distributions of each one to make sure that they're roughly right and the same, and know what the data that I'm dealing with is. Is it a bunch of zeros and some ones, or is it continuous, or is it normal-ish? That's the first obvious thing to start. But once you're past all those preliminary steps, I tend to make a PCA plot to look for such things, because I'm so used to seeing them. And even if I'm not told what groups they are, if you start seeing groups, then it's time to go back and ask what's going on. Like, what could possibly explain this? So a lot of what we do is we see these things and then we go, what's that called? Forensics, bioinformatics, I think they call it. And we try to find out how they killed the data. Yeah, and then there's some back and forth, and sometimes you figure it out. Sometimes you don't. I know many times you figure it out. Sometimes I remember this one time. This was interrogation more than forensics, where we were seeing a very clear batch effect, and it was so they had 4 and 4, 4 and 4 by control treatment, and when we looked at any kind of plot of groupings, BAPs, PCAs, whatever, it was 5. So it was 4 and 4, and we would always see 5 and 3. It's very clear that there was 2 groups, but this one was here. So we thought, well, they must have done it in different days. So we go and ask them, this is the interrogation part. Did you do it in it? No, we did it all on the same day. So we go and look more into it, and then we see that if you order them by hour of the day, they were done exactly like that, right? So these were in the morning, and these were in the afternoon. So then they get angry at the core and say, hey, how come you did this, right? You did. So then the core says, there's no way in hell that 11 p.m. and 12 p.m. are different. There's no way. So, and they show them all the kinds of other plots with the same, and they were right. It wasn't as strong as it was perfect correlation, but causation, right? It's not correlation, not causation. So then we kept interrogating, and then eventually it came out that before they even ran the high throughput experiments, they had done the experiments 3 and 5. That was nowhere. That information was nowhere written down. We only got it through interrogation, and it was like a 3-hour deal. Right, so they're like, oh yeah, we did these 3 on 1 week, and the other 5, but that doesn't matter. It's like, well, it looks like it does matter. But yeah, I'm just giving you an anecdote of the type of things that we have to go through to get to the reason for things. So it's never easy. No, sometimes it's easy, but it's not always easy. Not always easy.
Well, there was one anyway.
Also, the PCA is, you look at the outcome, right? So it's, and essentially how, because I always feel uncomfortable with PCA because you essentially, if you have one outcome, you run PCA, if you have another outcome, you also run PCA. And the PCA with the same data will give you the same result, essentially, right? So how do you deal with it? So do you run PCA in a subsample or something found, or?
Well, I mean, we're only using PCA basically as a way of. It's an exploratory step. Okay, and I hope that was clear. We're not using it to determine groups, to define clusters. It's just an exploratory that can show you high-dimensional data sets in lower dimensions, basically to see what's close to each other. That's really what we use it for. What samples are close to what samples? You could also make a plot of the correlations. It's similar. Like an image plot of the correlations is a similar idea. You're basically asking what's close to what samples are close to each other and which ones are not. So looking at the first two is not we go down the list. We don't only look at the first two. We go down, look at the first two, the third and fourth and fifth and sixth. To see if you see weird things lower in the dimensions. But really what we're doing is looking at a distance in a manageable dimension. Because these are vectors in 20,000 dimensional space. We can't make that plot. We can really only handle two dimensions at a time.
Do you rotate them?
What do you mean? The rotate what? Like if you're rotate what?
By rotation.
To the principal components? No. We transform the data and rotate the data sometimes, but not the principal components. But again, it's a very preliminary exploratory tool. If there's reason to think that they're not really showing distance as they should, then we might consider something else. Transformation. It's important to do a good transformation that gets the data into a form where PCA is interpretable. And so if you have data that's, so now it's say single cell RNA-seq, for those that have heard of that, it's new technology, relatively new, that produces data that's sometimes 80% zeros. Each sample has 80% zeros, so running PCA on that is not necessarily so informative. All it might be doing is just telling you which samples have more zeros. That's it. So I guess what I'm saying is, if you know the math enough to know what the data coming in needs to be for us to be able to interpret the PCA as we think that it should be interpreted. But no, I don't see why we would rotate the C's. Maybe there's a specific reason that I'm missing, but
Just to add to that, it will actually work through this after the break. We will have hands-on exercises related to this as well. So we'll have the chance to do this in the context of our IPRG data sets.
So, like this is maybe not super related to the batch effect or normalization, but it is related. I mean, it's more a complex analysis that I started with her. Like when you have, for instance, the group, like control and disease, like human some specific tissue. But in the tissue, you have like different cell types there, right? And in that specific case, where the disease is actually changing the cell type portion, like people start to talk about this, the decomposition of the gene expression, like using profile of the expression of these cell types to try to fix the bias that you would get if you do differential expression. But actually, I don't know if there is any package or analysis or like actually there is.
So that is, so what she's talking about is that in blood is a perfect example. Is that some tissues are a combination of cell types. I actually have an example I could show to you here, but I guess I can. So that everybody's on the same page. That that is a batch effect, and it is mathematically, it can be modeled the same. So you can use batch effect methodology to try to account for cell composition. So there's actually, I think there's a paper using like RUV to do exactly that. I'm going to show everybody because this is another big challenge in genomics that comes up very often. So these are a bunch of papers that I'll do it very quickly. All right, so there's all these papers that came out. I don't know how long ago, 5-6 years ago, and these are, I think these were the cohort studies. So when a new technology comes out, all the big cohort studies that have blood stored, they run all their blood samples on those new technologies and then publish a paper. But something I think that with methylation, when this happened, I think nothing was showing up as interesting. So you didn't see that many papers claiming that they found the methylation site for autism and blood disease and all that, and high pressure. But instead, you saw all these papers come out showing that they had found methylation sites that change with age. Because I think oh, hey, we didn't find anything with autism, but look, if we look at age, there is a correlation. So here's an example. This is one study, and they have thousands of genes like this. Thousands of genes where you've got methylation. This is one CPG site, one gene. If you don't know what a CPG site is, it's just like, you can think of it as a gene. It isn't a gene, but just think of it as a gene. So every dot is a person, there's their age, and they see that's a correlation. The p-value for that is very small. There's a clear slope. But look, if you look closely, the change. So methylation is a modification that can be on or off your gene. So it's a 0-1 thing. When you look at a group of cells, it's going to be an average of what happens in each cell. So it can be between 0 and 100%. So if you have a 0 methylation measurement, it means none of the cells were methylated at that site. If you have a 50% methylation value, it means half of the cells were methylated. If you have 100%, it means all of them. So here, the change, even though it's significant, the change is going from 8% methylated to 6% methylated. Okay, so here's a plot showing you a few genes, a few CPGs that have this. This is age down here. You can see the age. I'm going to show you the reason they're ordered the way they are becomes apparent later. But they're roughly ordered by age. See, this 2-year-old, 1-year-old, 4-year-old, 33-year-old, 3-year-old, 4-year-old, 3-year-old, and then here's 80, 37, 75. So they're older over there, younger over here.
Are those single sites or are they multiple sites?
Single sites. These are single sites. But what you see is that for these sites, there is this gradient. Right? So they were methylated when they were young, and they become unmethylated as they get old. So there's all these papers basically publishing these sites. They're saying all these sites change with age. All right, but now comes to her question. Blood is not a cell type; it's a bunch of them. So this is a plot showing you methylation profiles for natural killer cells, CD8, CD4, monocytes, B cells, and there's replicates. This is a very nice experiment where they took blood and they separated it out, and they took groups of different people. I think these are different people. And then you can very clearly see that the different cell types have different methylation patterns. I think that was known already, but there it is. So let me look at a close up here. Okay, so you see that's a close up where granulocytes and CD4 cells are very different. For these group of CPGs, granulocytes are off and CD4s are on, and vice versa for these. Very clear. That's going from almost 0 to almost 100. These are sites where the different cell types are different. Now I'm going to put these two next to each other. These are the same sites. And this is the blood. This is and look at that for a second and see if you see a problem. And see why it is kind of a batch effect. So an alternative explanation to this, other than methylation changing, is that when you're young, you have more of this. And when you're old, you have more of that. You see the patterns are almost identical? And then down here it flips. So this goes from red to blue, this goes from white to red. So what's happening, I think you already know what it is, it's not that methylation was changing, it's that your cell types were changing. And you can think about mathematically as a batch effect. These guys are correlated with each other because they have more CD4s. These guys are more correlated because they have more granulocytes. So yeah.
Doesn't single cell kind of remove this pooling effect that we've seen in sequencing in general?
It should.
But it creates a whole sort of other problems in processing.
A whole nother set of problems, right? Yeah. Well, that'll get better. Well, anyway, so one thing you can do is you can estimate the different cell types from the data, and you can see that that's what the ordering here was the percent of granulocytes. As you get older, you get more granulocytes. So now the main point, and here's where you can really see that it's a batch effect. That this is not cartoons. These are data. This is data. This is actually numbers from the data. So this is a young person, and that's their profile, blood profile. This is an older person, and that's their profile. Okay, so very different. Those are different profiles. Very different. It's blue. That's red. Now, and so you can say methylation changed, or you can say methylation stayed exactly the same. So notice that this and this are the same. This is the profile. These are all exactly the same. No changes in methylation. But by multiplying these groups by different numbers, okay, so here the big difference comes here, where granulocytes are high and low. You can generate these profiles. Granulocytes high and low. You can generate these profiles by combining the cell types. So that's ultimate. So how does this the batch effect? What the batch effect? The way to think about it as a batch effect is that these would be the factors that get you estimate these values, and then that is accounting for the cell differences, and then you try to get to the actual differences that are left over. So mathematically, you can try to use these RUV thing, RUV or RUV.
So to estimate these values.
So the RUV will automatically try to find these things.
Okay.
So here we have the advantage that we know the profiles in advance.
Yeah.
You might not have that. Right? So let's say you didn't know these profiles. If you didn't know these profiles, you have to estimate them, and that's what factor analysis does. All right. Yeah.
Around slide 43, you presented a heat map decomposed into sex, month, and non. How would you go about producing this? Is it you plot by?
Oh, how did I make that plot? Okay, so yeah, that's the code is all available, by the way. So a lot of these things are in a book that I wrote called Data Analysis. Oh, wait, no, this is in the book. Data Analysis for the Life Sciences. It's free, and you can also get the code that I used to make the book. So if you go to my webpage and go to publications, there's a link to the actual book and the code. So the code for this picture is there. You can just go and grab it. But how did I make it? So this is just the data. This is, I estimate, I have my X matrix is, I have 1 for the reference and male or female, so it's 1s and 0 1s, depending on, so each sample either gets a 0 or 1 for male and female. Matrix multiplied by the estimated betas to tell me the difference between males and females. So it's a 2 by 12 matrix multiplied by a 12 by, I'm sorry, the other way around. A 8,000 by 12 by 2 matrix. Those are the parameter estimates for each for each gene. Times a 2 times 12 matrix, that's the design matrix, gives me a 8,000 by 12 matrix. And that's what this one is. This one is the same, but for the factors. So I have a 8,000 by, I don't know how many factors I used here, I think 5 by 5 matrix, and then a 5 by 12 matrix, and that gives me. And then this is this minus this minus. So I mean, that's how it's done. There's in R you can get these things with like predict I think, if I remember correctly, I just